so they'll pick up in a minute. We had left with this discussion of stimulated emission and these probabilities. So, three processes: we can spontaneously absorb, we can spontaneously emit, and we can stimulate emit. And the one that we care about, really, is the stimulated emission because it has the special properties of light that we want. Now, before we got here, when we just talked about absorption and emission, we never put the word spontaneous. They just happened. We just never felt necessary to distinguish them. The only reason we're distinguishing them now is because we have the two process here. It's very unique and it has very unique properties. So we'll get back to these probabilities in a minute, like the book did. But first, why we like stimulated emission, what we can get out of a laser. So, laser light has a set of properties, four of which are really important. First, it's monochromatic because it goes between two energy levels. It has basically a single wavelength or single color. And that's not the same if you heat a filament. A filament has all sorts of colors. It gives a broad spectral line. This thing doesn't. So, for instance, I could use the color to encode information. I could match the color of the wavelength to a particular biological process, for instance, to cut skin or to kill a cell, or to actually attempt to detect a specific molecular species like anthrax. Whereas if I put a regular non-monochromatic source, then some of it would go to what I wanted, but most of the energy would go to something I had no interest in. For instance, damaging the cells or something, rather than just producing something that I can detect. So that's one of the advantages, is that it is single colored. Okay, it's monochromatic. Number two, it has high intensity. You can get a lot of light out. That means you can use this to cut things. So you have some choices. You could, for instance, vaporize a cell, literally, and use this as a knife. People do. So use a surgical knife. Or they can run an optical fiber inside of you, of ways that you may not wish to know about. But inside of you, rather than cutting you open, for instance, and get into your bladder and blow out a stone. Whereas before, that stone was in there, the only way to do it is start cutting into it or get into your kidney. You don't have that anymore. They can stick it down your throat to get down and to destroy a tumor or such, rather than having to open you up with a knife. So the fact that you can stick an optical fiber that's, a few millimeters thick and attach a laser to it and put that energy anywhere you want means you have a surgical precision you didn't have before. So high intensity, if you want to do machining, you want to do manufacturing, lots sorts of things you can do there. It's unidirectional. It means it goes in one direction, so all the energy goes the way you want. This has to do with something that you have to build in the way you set up your laser, but you can shoot a laser all the way to the moon and bounce it off a mirror without the mirror there. We actually measure the distance between the Earth and the moon. You can't do that with a regular light source. It spreads out in all directions. This thing doesn't. And last but not least, maybe the most important and the most abstract for students, it's coherent. That means it's in phase. In phase means that it is perfect for all sorts of interference type phenomena, either to test, for instance, to test the nature of quantum mechanics, or to test the nature of other things, or, for instance, barcoding, or for using any sort of other thing like holography. Anything in which the information is contained in the phase, a laser is an easy way to do that. In the old days, to try to create coherent light sources was not trivial. Thomas Young tried to do his double slit experiment. That was a challenge. That's why people hadn't done it before. Regular light is not coherent. It's not in phase. You don't get all the interference effects because it has a random phase. Not so with a laser. Yeah.
What's holography?
Holography is when you actually split a laser beam up and bounce it off an object from two different paths. And when the light comes back onto the film, it puts the interference pattern. If you shoot a laser back through that interference pattern, it'll produce a three-dimensional image of the object setting up in space.
Huh.
So if you see these little things on your, for instance, credit cards that you turn around and they move around, that's a hologram. And these things, for instance, are very difficult to reproduce, impossible to reproduce on, for instance, a copier. So this is one of the things I want to do with money, to make where you can't steal money. You may not think about it, but coupons are also worth a small fraction of cash. People photocopy coupons and put them back. They want to prevent that as well. So holograms are used in all sorts of interesting applications. They're in your book. We won't do much more with them. I've got the film and such to make holograms. Vibrations will kill them. So you have to figure out how to make it. I made my own holograms, built my own hologram deck when I was in high school. It's a real challenge to make a hologram. But it would be impossible without a laser. Now you just have to get rid of all the vibrations to get some good fast acting things. So anyway, these four things enable us to do all of the optical computing. They enable us to do all of the fiber optics that we do today. All of optical communication. They're absolutely an essential part of why we like a laser. Laser has unique properties, and these four are them. So you should know the four properties of laser light. Long before there were lasers, way before there were lasers, Einstein worked out the AB coefficients, like 40, 50 years before there were lasers. How did he do that? Well, what he did was he just sat down and said, okay, let's start with some facts. The first fact is we'll just take a two-dimensional system. I should say two-dimensional, two-level system. So I got a bunch of red balls down here in the lower energy state, and I got a bunch of blue balls. These are atoms excited in the higher state. And Einstein says, okay, let's assume for a minute I had a system that was in equilibrium. Why? Because he wasn't looking for lasers. He was looking at how atomic physics of heated objects and other objects respond, and he was interested in this idea of photons. Okay, so lasers happen to deal with photons, and lasers happen to deal with these processes, and so that's the reason Einstein's work overlapped. But he wasn't trying to build a laser, he's trying to understand atomic physics. So he has these lower level guys, he has these upper level guys, and we talked about last time, the probability that the red guy goes up depends upon the number of incoming photons that has to be there. If there are no photons, it can't absorb any energy and go up. The number of red balls that I have down here. The more red balls to absorb photons, the more likely they are to go up. And this probability that's based upon the absorption between those two levels, which I don't know what is at the moment. In fact, that's what I want to find. So that's the probability, or the number, if you would, really, the number that are going up. It's based on these facts. And the number that spontaneously come down depends on the number in the high level. So if there are no atoms in the high energy state, none can come down. And this probability that a single one of them will come down. That again is from last time. And the last thing we had last time, the probability by stimulated emission depends on the number of blue guys, depends on the probability for stimulated transition, this B2 to 1, and of course the photon, because the photon has to come in and stimulate it to fall. Now what Einstein says is, okay, we have equilibrium. If it's in equilibrium, the number going up has to equal the number going down. So all I have to do is take this and put it equal to the sum of the two ways it can come down. There's nothing more that says the number of balls going up has to equal the number of balls coming down. Otherwise things are going to change. And I said it's an equilibrium. I said things are not changing over time. So I take that equation here and I write it on the left-hand side. And I take these two equations for the number of balls going down, the blue balls, and I put them over here. And then what he says, okay, hold on here. I want to solve for this energy density of photons, because remember he was really interested in that. He was interested in Max Planck's work on that. So he says, if I want to get all the U terms together, then I need to move this term to that side of the equation. So he does that algebra, and he factors out the U. So there's the U, and I got an N1B12. Those are going up. And then I got to count the ones that are falling down by stimulated. That's this one, which I moved to the other side, so minus N2B21. And all of that has to equal what's left over by spontaneous emission. And then he says, okay, I'm going to solve for this. I'll just divide both sides by that algebra term. Now, if you stop at that point, the problem is, it looks like every term's got a lot of stuff in it. It's going to be hard to figure out what things are. For instance, N2, the number of atoms is in the second, and then I'm multiplying by a constant I don't know. And then N1, the number in the first region, which I don't know, times B12, a constant I don't know, minus N2, which I don't know, times B21. I don't know the individual values N2 and N1, but I do know their ratio. Their ratio is governed by the Boltzmann distribution, so I do know that. So the point is, I don't know N2, I don't know N1, but I know this. That's the energy over KT. And I know the energy. It's this energy right here, which is the same as the energy of the photon HF. So this is e to the minus HF over KT. So what I want to do is I want to get everything to have N2 over N1 in it. Well, the top has an N2, so I'll divide it by an N1, I'll divide the bottom by an N1. So I get N2 over N1, the N1 cancels here. And I get N2 over N1. And now everything still has the same constants, but I've solved the whole problem for the N2 N1 because I got it set equal to this. Now I have assumed something. I've assumed these are not degenerate states. Okay, there's not like 12 states of that energy. Okay, I've assumed their G's are 1. If you don't like that, look in the particular one that y'all have for Survey doesn't deal with it, but certainly Roth does. All right, as you would expect, he's dealt with that as well. So I got N2 over N1 times A. I don't know A. I got B12. I don't know B. I got N2 over N1. I want to replace these all with this exponential function. And while crunching on a Subway sandwich, I made that my Subway sandwich for lunch at 11 o'clock was okay. I got the following. I replaced that with e to the minus HF over KT. And I applied this with b to the minus HF over KT. And I got two exponentials. I can improve that a little bit. This is minus. I could just bring that to the bottom and it would be plus. If I do that, it'll give me an e to the plus HF over KT here, but it will cancel that one. So I do that. Nothing but algebra, but it makes the formula look a little better. Still got three unknown constants. I know HF because I know the energy levels. I know KT because I know the Boltzmann constant, and I know the temperature. But I have three constants here. And I don't know U. Now, I didn't assume anything other than this system was an equilibrium process. So it has to hold for any equilibrium process, Einstein says. The equilibrium process that he most cared about at this time was the black body radiator that Max Planck had worked. So he says, hey, any process works. So why can't I just use a black body for U? Because that's been shown to work. We know what its energy density is because Max Planck did it. So I can put in the value for this into here and then see if I can evaluate those two constants. So let's see what. So if you do that, here's what Max Planck said. So this is a long time ago in a galaxy far, far away, called the first part of this semester. Thank you, Mr. Max Planck. So he takes that and he puts it over here. Now, if you look at that, that side here looks an awful lot like this side, especially if I, for instance, bring the A out. There's something times an e to the HF over KT minus something. Over here, there's EDHF over KV minus 1. Now, that thing looks exactly like, the only way these two could be the same is if this B here was the same as that B there. It doesn't have to be 1. If these two are the same, I can factor the B out front. But it does say that this B, the probability for absorption, has to be exactly the same as this B, the probability for stimulated emission. So if you want to have something that has good stimulated emission, it's also got to be something that wants to absorb light. So when your photon comes in and you think, well, I'll just get something that wants to stimulate but doesn't want to absorb, that's not possible. The more you try to make it want to stimulate, the more it also wants to absorb photons and take those photons away. Yeah?
Is this only the case for black body radiators?
No, because these constants are constants independent of the temperature. Therefore, they have to hold for all cases. The fact that they are constants and the fact that this equation up here is true, this equation has to hold for everything, including this. So those constants have to be universally true for everything. So though Einstein never had a laser, because he worked on the black body radiation, he's able to find the AB coefficients, and they're called Einstein's AB coefficients for lasers. This is the so-called semi-classical approach to laser physics. There is a quantum approach, far more complicated, that was developed by Land and Scully.
Scully, the one that gave
And
this
Scully is the one there, and Land is in the Nobel laureate, Willis Lamb, who was his thesis advisor.
Yeah.
That's right, he did the first quantum theory of a laser. So, this B and that B has to equal, and they're usually just given a single B, and they throw away the 1, 2, 2, 1 since it's unnecessary. Now, if you do that, then you can rewrite this. As that. You can factor a B out of here, and then the E to HF over KT minus 1 is the same as that, so A over B has to equal all this junk out here. And that means you can take and multiply that B by that, and you get this requirement for A. So I can't eliminate all the coefficients, but I can eliminate it down to 1. And it says that the spontaneous emission goes up with the frequency cubed. So the higher the frequency, the more likely it is that this thing wants to emit quickly by emission. That makes a lot of sense. High energy photons don't stay there very long. That's exactly why, in the fact that you don't get this, you get this fall off of high energy light. With those coefficients, people can and do design laser systems. All right? But it is certainly a classical system. I didn't see no Schrodinger equation anywhere in this thing. We did quantize light and talk about it kind of a photon, so semi-classical, but I haven't considered the wave property, for instance, of states, and I've only considered a two-state system. In particular, I've not considered the possibility that you might have something like this, in which you could have maybe this possibility, which there may be two absorption states pretty closely matched and one emission state that dominates. Or an emission state, for instance, that goes to somewhere else, even to a lower state, or to another state over here. Why would I like that? It's possible, since these are waves, and these probabilities act as waves, to get the probability of absorption here and the probability of absorption there to destructively interfere. And so even though there are all sorts of guys here that could absorb, they won't. And you can get lasing without inversion. Also, an idea of Steve Harris at Stanford that was also in conjunction with Scully and for which he experimentally verified at Texas A&M. It's not a lot of usefulness yet to this, but again, it shows you something that classical physics leaves out a lot of stuff. It always leaves out all this wave phenomena. There's all sorts of interesting things and statements that says you can't do this. And then quantum mechanics says, you want to bet? Yes, you can. And not only can you do this, but you might even be able to make it useful for something. So quantum mechanics always gives us more than the classical or semi-classical stuff does. Now, given that I said this absorption and stimulated emission things are connected and you can't increase stimulated emission without absorption, then you have to go back and look at those probabilities again. So here's the absorption, each of my photons. And this is the one I want to create photons. And if it's going to be an amplifier, I got to get more out than I put in. Well, they both depend on U. They both depend on B, which we said is the same. So the only way this dominates that, semi-classical with only two levels, is if N2 is greater than N1. That means there's got to be more atoms or electrons or whatever you're doing to excite have to be in the high energy state than in the low energy state, and this is not the norm. You lift things to high energy, they fall down, right? And in fact, they fall down pretty quickly, you know, if you try that. So, for instance, kind of stupidly, but it works. You know, you take something and you say, okay, I'm going to take two things, I'm going to raise them to a high energy state. When you raise one, no matter what you do, they keep falling back down. And that's because these are what are called regular states. These states have a short lifetime. Most things are regular states. You never build a laser out of anything like that, because as quick as you could try to pump energy in to get it up, it's going to come back down. And you're never going to get more in the top state than in the low state, and if you don't get that, you're never going to build a laser. And that's one of the difficulties. So you can't take a table, for instance, at least in equilibrium thermodynamics, and build a laser, because you never get inversion. So, these are regular states, and going by what some people put on the websites, and you can look around, some people would like to say a regular state de-excites in a short amount of time, less than 10 to the minus 7 seconds. I would almost not declare that anything that's that long as being a regular state. Most regular states de-excite in like 10 to the minus 12, 10 to the minus 16 seconds. Okay, so a tenth of a femtosecond, maybe an attosecond, a picosecond. They generally don't stay around that long. So regular states de-excite quickly. So you're losing a game, just like I would be, to try to lift everything on my desk and stick it up in midair and try to go and get another thing and stick it up. I'll never get all the stuff on my desk up in a high energy state. Of course, there are states that don't behave this way, even in the table. So for instance, if you had a bunch of stuff on the floor and I just lifted it to a random spot in the space, it'll fall down. But if I stick it on a tabletop, that's a long-lived life state. Now, if the tabletop is bouncing around because of an earthquake, well, you mean like the uncertainty principle in energy? It's moving them around in essence, changing the energy slightly within its amount of time. Then it might eventually fall off, but it'll stay there quite a while compared to just lifting it into mid-space. These are what are known as metastable states. And by the way, to kind of show you that, I got a vibrating plug here. You can see this sharp little peak. And you might be able to argue, you've got some little rounded edge that you can put a ball up there. But if I bounce that table like I would with the uncertainty principle, getting bathed with photons banging me from around in the environment, as well as just the uncertainty and energy anyway, this thing is not going to stay very long. It's going to get stimulated and come on down. I shouldn't say stimulate, bad choice. It's going to spontaneously fall on down. In a metastable state, you can think of it kind of like it's got a little hole in here with some humps. And so it's kind of in a minimum. And it doesn't want to go there. But again, if you shake it enough, it'll eventually roll out. It'll get enough bouncing back and forth till it comes out. But it'll take longer, maybe on the order of a millisecond to a microsecond. So these states live long enough that you can push electrons or atoms in some excited state up to these states and stick them, whether it's a molecule or whether it's the electron you want to consider electronic transitions. You need one of these. If you don't have one of these, you'll never get inversion. So you can't make a laser out of just anything. It's got to have a very special material. It's got to have one of these special quantum states in it. Now, There are people who spend a lot of time going around looking at every possible state and measuring its lifetime and so forth. They're called graduate students. All right? This is what theses and PhDs are made on. And from these come all the technology that drives all of engineering. Because without them, you don't build anything. All right? So you got to have these state maps. Some people sit around. One of the things they're interested in right now is oxygen and nitrogen transitions, because you might be able to create a laser in air. Why do you want to do that? Shoot a very powerful laser in the air, create a laser filament, then shoot a particular filament that causes a transition for some trace element. For instance, it might be uranium fluoride, because you're looking to see if somebody's processing uranium inside a nuclear reactor, which they're not supposed to be. And then, because you created a filament in midair, it acts as a mini laser and it concentrates back the signal to your detector, so you can measure incredibly small concentrations. One of our former graduates actually is helping work on such a project. All right? So there are all sorts of applications of lasers in gases, solids, solid-state devices, so forth. Take your imagination, let it go wherever. But all of them that I know of, although it's possible to do with lasing without inversion, every one that I know of, every practical one, is an inverted laser. So they have to have one of these metastable states. And you have to know the energy levels if you're going to be able to study the laser. Population inversion, just for your book, or for your notes, when you have more atoms in the excited state than in the lower state. And to achieve that, you need a metastable state. All right, so we basically got everything that we need to do a laser now. We know about metastable states. We know about stimulated emission. We know about spontaneous absorption, about spontaneous emission. And now the question is, I want to go build one. I don't just want to talk theory now. I want to go build one of these guys. You know, how did Towns, who I was fortunate enough to meet a few years ago, how did he invent such a thing? And in fact, he invented a maser. It was easier to do this in the microwave region. So how do you build one of these things?
Can you do this in lab?
Huh?
We can do this in lab?
Can you do it in the lab? No.
No.
There is a group of people in the state of Texas, and if I was going to do it, I sure as hell wouldn't tell you we would on television. There's a group of people in the state of Texas in laser radiation safety, and you would be violating the law, and we would go to jail. All right, so you can't just go build a laser. Lasers are actually regulated just like accelerators are. All right, any more than you're allowed to build your own reactor in your backyard just because you think about it. I don't know if you guys have read the story of the radioactive Boy Scout that got it. Actually was building a thing generating radioactive nuclides that created such a problem in Michigan some years ago.
I think I have heard of it.
They thought he was sneaking the stuff out at night, and they thought he was like stealing hubcaps or something. Far from it. He had basically a Superfund waste dump they had to clean up from all the radioactivity. So never know what the boy next door may be doing to your property.
So they have a thing in Texas
Huh?
that they have a commission that makes sure that we don't build anything like this?
Okay, yeah, it's against the law.
I don't see
They're
a
coming to
harm
haul
to
you
it.
in. You can't just go build a laser and you put people's eyes out or kill them.
Oh,
There's a whole series of requirements. So
yeah, I see
no,
that.
you can't just build any laser you want.
Oh.
Now, to build, so let's assume we're going to work for a company for a minute. So we're not in violation of law. All right. Then to build one, you're going to need a pump source. Okay, the first thing you got to do is you got to pump energy in. You can't violate conservation of energy. You don't get energy out without putting something in. So you got to pump energy in the system to get those atoms up to an excited state. You got to have a lazy medium with a metastable state. You need an optical cavity. You need some sort of a cavity. Why is that? Because I'm going to want the light to come out in a single direction. Okay, I'm not going to want it just coming out in any old way, so I'm going to want to direct it. And also, I'm going to want to cancel out any waves from other processes besides stimulated emission. For instance, spontaneous absorption emissions. I don't want them to show up, so I can do that with a cavity. And last but not least, where you want to get the light out of somewhere, you better have an exit window. You've probably got some optics, because you're going to want to focus it or do something else with it. So, first things first, you've got some sort of a lazy medium here, and you can put any type of pump source you want. Usually what people do is they use some gigantic flash tube, and they do it by optically, because that's the easiest. But hell, you could just put a big heating source. Okay. You might laugh about that, but there are lasers in the military that vaporize, use engines, like jet engines, and they can put holes through this building with the energy that they put out of their lasers. They're designed to annihilate things that they hit. All right. But you need some pump source. There's your laser medium. And what we're going to do is we're going to put some sort of a mirror over here. And some sort of a mirror over here. And there's some distance between them. And that's an optical cavity. That's a particle in a box, in essence. Okay? So the electric field has to be zero, and it has to be zero there, and that limits the wavelengths that you can have inside of this. And it's very sensitive as you adjust that cavity back and forth. You change the wavelength. And then at this point right here, there's a window, and that window doesn't let everything out. It's usually like a 1% to 2% pass window. So here's the idea. We excite all the atoms into, or at least some of them, up into the upper levels. And then we get a photon. How do we get a photon? Spontaneous emission. Sometime in this thing, a photon will get emitted just by spontaneous emission, and it'll be going, it'll have exactly the right energy because it's from the two levels that we want to get stimulated emission from. And it has some probability, maybe not much, of interacting with these atoms. So as it goes along here, maybe it picks up another one in phase. Hits this window, this part of the mirror, bounces back, de-exciting and picking up more photons. Hits back here, back, forth, back, forth, back, forth, back, forth, picking up rebels as it goes. Now, you're pumping energy in. Some energy is being lost. If you're pumping more energy in that's being lost, this is growing. At some point, as it grows, more energy gets out. At some point, the amount of energy leaving and the amount of energy going in reaches a balance, and that becomes the amount of energy you get out of the laser. You don't have this, it's a single pass, you don't get much out. It's also not going to be unidirectional, and it's probably not going to be coherent because you're going to get other processes. You don't have that, nothing works. You don't have a metastable state, you just absorb energy. And it randomly sends it out. Right? You'll never get gain. Right? If you want gain, you've got to get inversion. Yeah?
What's an example of a metastable state?
All sorts of atomic metastable states. Carbon has metastable states. CO2 has metastable molecular states. Helium has metastable states in the heat laser. They are simply atomic states that look like everything else, but they live longer. Probably because the transition has some set of forbidden quantum numbers, like it can't do a dipole transition, it does some other transition. So does not have a very high probability of transition because the wave functions, the integral, remember those probability integrals? It's small. Yeah.
So if I was to go to the gas station and buy the laser pointer they have there, would I see the same
That
thing?
laser pointer specifically, it probably is a solid state laser, but I'll show you one right now. I got one on here. Unfortunately, you can't plug it in because where our power supply is. This is a standard heating laser. So if you look inside here, you've got a metal side over here and over here. That's your optical cavity in here.
Huh.
All right. This stuff back here, this is to generate your power supply. And the way this one works is it don't heat with a match. It smashes electrons into the gas molecule and excites them by electron impact. So there's a gas in here, and between those two leads is high voltage. So the electron flies across and smacks into them with high voltage. And that's how you excite the gas. You get the high voltage, you got a ballast on the other side. generating the high voltage for that.
So can the lasing medium be something other than gas?
Sure, solid state routing. Neodymium YAG. A lot of solids have it. But you gotta have a metastable state in whatever the system is.
Would a diamond be like a metastable
I
state?
don't know of any diamond states, but that doesn't mean they're not. For one thing, a diamond is a rather expensive little device and it has to be very pure and they're hard. And how are you going to get a very large crystal of a diamond? Okay, large crystals of diamond are known as very expensive.
Huh.
It'd probably be more likely to be stolen by your girlfriend before you get it in your laser. So, if you, well, in your case, you'd say. The rest of us will not have that trouble.
You ever seen that Batman movie when Mr. Freeze comes in and he steals all the diamonds and he puts them on this laser to freeze the
Fortunately,
city?
I've managed to miss Arnold Schwarzenegger in that movie.
Okay, 'cause see, that's what I was thinking. I was like, I don't know if that would
I'm
work.
more likely to be watching the History of Science channel. I'll leave the Batman movies to you. Yeah.
The like an indie YAG, they grow those in they grow those crystals, right?
Yeah, well, they have to grow them very,
Especially.
well, they have to grow them perfect. Very few defects. The defects affects the energy levels, and then it doesn't work. So a crystal is tough. On the other hand, a crystal, you can put a lot into it. Now,
Really
the biggest one are these big gas engine type things at the Army that are non-equilibrium. But there's a problem with gases. They're one shot. They're so powerful that when they shoot and hit the mirror, they vaporize the mirror. So it's a one-shot type thing. Of course, the most powerful lasers are the ones that need a little bigger pumps, are called a thermonuclear warhead in Star Wars. So you had these unidirectional lasers, and then for a pump source, you set off a hydrogen bomb. And then that would set off the thing and shoot all the little missiles, but of course then vaporize the materials that you had. So they don't last very long. You can't use a metal. They have very special materials that you're not allowed to know about.
So if we were to build this for a capstone project, we couldn't build this for like a capstone project.
For a classroom project,
Yeah.
no, not without appropriate licensing and such to do these things. And if you look around, there's things that say avoid exposure and such. There are different classes of lasers, and what you have to have depends on the type of laser. Okay, a class 4 laser has some stringent requirements because you really can't take a, the old statement is, now look at the laser beam with the remaining eye, because you literally can't explode your eyeball. Literally boil it to thousands of degrees and it explodes. Okay, and that's not by looking at the light, that's because somebody accidentally put something that was shiny and it happened to deflect and it bounced back into your eye. And I don't mean it has to be shiny like a mirror. There's so much energy, it doesn't have to be that shiny. It just doesn't diffuse enough if it goes in your eye, so you should always have your goggles on. The problem is when you have your goggles on, you can't see anything if the laser's not on. So you end up having to take your goggles, over, try to find your way in the dark. If you turn off the laser, turn the lights on, take your glasses off, put them back. And then people don't do it, and the one time they don't do it, they get zapped. All right, so this is serious stuff, just like accelerators. Radiation is ruled and covered. If you want to use one of these for medical and elsewhere, there are rules and regulations you have to follow. Now, let's assume we want to build that and we got all that. Well, then you got some choices. So there are 3 types, but only really 2 practical ones. The 2-stage laser. Now, this is the way we think about them, but it's not practical to build. All right, from an engineering standpoint. You have just two levels. Now, there'll always be lots of levels in the atom. I'm saying you're going to build it to try to make this thing run off just these 2 levels, not use any of the other levels of the atom. So here's the problem with the 2-level laser. You have a pump transition, and you have a stimulated emission. This is the ground state, probably. This is the pump state. So if you try to optically send photons in, pump this, if you want to make this metastable, it also doesn't like to be pumped up. And it turns out that you can't get an optical source strong enough to pump it. So if you build a 2-level laser, you can't use a flash bulb or something like that to pump it. And that's the easiest way. You have to build some sort of electronic accelerator in there like the Heaney has, or you're going to have to build something else. So that's a serious disadvantage of these guys. And the second thing is to get inversion up to here. That means here's all these guys, you have to pump 50% plus of them up. Well, that's like 50% of the universe. That's going to be a real trick. Right? Now, maybe you could find a way to do it. I'm not saying it can't be done, but it's going to be an extremely low output source. like absolutely puny. So it's just not a practical thing to do. Things you should be able to lay. That's the ground state. That's where you start. That's the pump state. That's where the pump ends. That transition is called the pump transition on all lasers. The top laser for the stimulated emission is called the high-level laser state or the metastable state, because it's got to be a metastable state. And the bottom place for the stimulated emission is called the low-level laser state. And that's stimulated emission, so we would hope that you see a photon coming out of that thing right there, and if I knew these energies, I could tell you what that photon was. It so happens that that photon energy matches that pump state energy. So these two facts make a two-level laser not practical. So what people do is they don't do two-level lasers. They go to at least three-level laser systems. So here's what a three-level laser is. Well, it has three levels. All right? The ground state, pump state, and this high-level laser state. So because this is not a metastable state, it can be a regular state that likes to emit but also likes to absorb quickly. So what you want to have happen is you want to pump this thing up, and before this state normally goes back down like this, by spontaneous emission, you want it to quickly do some sort of electronic transition, maybe give its energy to vibration of the atoms or something in phonons, and end up in this state. So you pump it up, and then hopefully get it over here. And it gets stuck. That's the traffic jam. That's the metastable state. And you pump another one up, stick it. Pump another one up and stick it.
Did you say phonons?
Huh?
Did you say
Phonon. Energy levels of sound or vibration inside a crystal. Not only photons, there are also phonons in solid state. Any type of quantum that's got an on. You know, there's persons, protons, electrons. All right, these are phonons. So some non-radiative transition. It gives us energy by some way other than light. Because you don't want any other lights in there if you can avoid it. And you want it to be fast so that it doesn't give it up back this way. Then you also make your cavity so that it cancels that type of light. So it can't build up in there. Okay? You want to emit it out. You make it so it doesn't match the cavity requirement. But you make it match this cavity requirement so they can build up standing waves inside. Then you get your stimulated emission, which is energy is this, which is less than that. Right? The emission energy went off here. So again, all the same things. The difference now is the high-level laser is not also the pump state. So now you can optically pump it, but the downside is you still got to pump more guys here than in the ground state. So you still got to get this like 50% type stuff. But because you can optically pump it, it might be possible to do that. And it is. The heating lasers and them that are very low powered, your pointers that you have, that's what they most likely are. They're three-state lasers. They're low power lasers. Well, damn it. The problem is this stupid guy here. If I just didn't have to pump all these guys, I could get inversion easily. Well, guess what? Four-state laser. These are where the bad boys reside. All right? In the four-state laser, you've got a ground and a pump state and a pump transition. Then you have a non-radiative fast. And down here you have a non-radiative. But here's the advantage of this guy. Got all those guys there. You pump this guy up to here. So he disappears and he goes to here. Then he drops down to there. You've already created inversion. Because there's more than down here. So you instantly obtain inversion. You can optically pump it, you can get inversion, you can get tons of photons out, for the power that you put in. So the more power you put in, the more photons you're going to get. This thing has the ability to make, these are the YAGs, these are the krypton lasers, these are the guys that can literally blow holes in things. All right? They don't have to, but they are the ones that have the potential for that. So the problem originally with the two-level laser was the ground state and the low-level laser were the same, and the pump state and the high-level laser were the same. In the 3 state, we broke the pump in the high level, and in the 4, we also break the low level on the ground. This is a practical laser. And you still got to build your cavity, you still got to get your pumping system, but you need a system with 4 levels that you can work. So you need some excited level transition here between a metastable and a regular, fast, non-radiative transition. So you need to know that you can do this non-radiatively. You need to know you got one of these. You got to make sure this happens really fast and quick. And you got to have this be the right energy that you want. Because nature makes these. You don't get to adjust these levels. Yeah. Can I change them slightly? If they're molecules and they're in bands, say in crystals, I can dope the crystal. And by putting some impurity atoms, I can change the environment electric fields around, and I can adjust these levels slightly. And so, yes, I can build a blue level laser LED if I want for my display or by doping it, or I can make it move toward the infrared. Why would I want blue? I'm looking at interference patterns. The smaller the wavelength, the more stuff I can cram in. So we're all moving to ultraviolet because you want to have more stuff on your movie disc. Because you want more stuff on your movie disc, it's got to occupy less space. If it occupies less space and it's an up or down, for instance, a bump on this disc, then I need an interference pattern I can read, and I can't do that unless the wavelength is smaller than the size of the object I'm looking at. So that means I need smaller wavelengths. So that's why we're going to ultraviolet DVDs, and we'll continue moving down. Now there's a problem with that. At some point we get to X-rays and such, and when we get to X-rays, then we'll have the issue that the stuff will go right through the material. And that'll be a problem, because then we'll get signal back, right? Also, X-rays are known to be harmful to human cells if they're made wrong. So there are some issues about that. But if you look at it, we've started from things and have moved down. On the other way, if I want to shoot across the room, I want it to bend around any obstruction, like my brother getting in front of me. Well, I did television, so I like long wavelengths if you prefer. So infrared tends to be a preference for building control devices. All right. You can really build almost anything you want if I can find the right type of metastable state. And that's what I do. I search for metastable states. Where are we at? I think we're at a pretty much a perfect place to time, except for the one fact for here. We have an exam this week. You guys have to pick a date.
Friday.
Your choices are Friday or Wednesday.
Friday.
Wow.
Friday's
Okay.
great.
Friday at 2 o'clock it shall be. Come prepared. I certainly will be prepared to attack you. I'm going to be prepared to defend.
Will we have lasers on this test?
No, I took them off. Because we did not cover that last week. I've taken off anything that exceeded what we were. The molecule stuff about rotation and vibration, like the problems I've worked, nothing else, is the last thing that we will have. But know your differential equations, no eigenvalues, no operators. If we covered it, I expect you to know math. This is not a freshman course. You're supposed to be with me. So make sure that you know how to do all that stuff on the notes and in the test your knowledge problems. It'll be comprehensive as always. Okay? All right. See you later. Review. Any questions?